Hello, everyone. My name is Ken Christensen, and I'm the Carolyn Ed Kaplan Dean of the Armor College of Engineering at Illinois Tech. Welcome to the Armor R&D Virtual Expo, showcasing the work of students who participated in the Armor R&D program for fall of 2021. As I've come to appreciate, the Armor R&D program is a distinct development of an armor engineering education, giving undergraduate students the opportunity to gain hands-on research and development experience in the lab of a faculty mentor. I'm proud to celebrate the accomplishments of these students during fall 2021, and I also offer my deepest appreciation to those faculty and graduate students who provided mentorship to these students. If you haven't yet taken advantage of the Armor R&D program, I encourage you to seek out a faculty mentor and submit a proposal for the spring 2022 semester. Our faculty welcome undergraduate students of all levels and experience into their labs through this program. I hope you enjoy the excellence showcased in this Armor R&D Virtual Expo, as much as I know I will.
Hello, everyone. I hope all is well. My name is Maciej Derula, and I'm a second-year mechanical engineering student. This semester, I've had the opportunity to work hand-in-hand with Professor Mustafi through the Armor R&D program. In a broad sense, we focused our attention on looking to contribute to the understanding of densification kinetics of extremely fine stainless steel alloy powders during printing. This helped contribute to research surrounding binder jetting while also propelling binder jetting onto a larger scale because its high throughput has a low cost and is much more energy efficient. Studying challenges surrounding densification correlates with energy efficiency in the manufacturing sector. This is crucial as the lack of resources may prove disastrous for production of parts with any purpose in the near future. As a general overview, the goal of this last 10 weeks was to build a solid understanding of densification kinetics of ultra-fine stainless steel binder-jetted 3D printed alloys. The proposed work was aimed to advance the state of technology on binder jetting of ultra-fine powders, incorporated with an innovative manufacturing system of using ultrasonic powder dispensers to enhance powder packing density while also minimizing powder bed defects. Optimal process parameters were used to 3D print stainless steel 316 low carbon feedstock with an average particle size of 8 micrometers, followed by sintering. Various sintering parameters and holding times were selected to study densification kinetics and resultant microstructure and phase formation in consolidated parts to achieve a density of greater than 99.5%. To begin, binder jetting is a 3D printing process that shapes parts layer by layer using a polymeric binder and powdered materials using the X1 Innovent printer, as shown in Figure 3. Amongst other additive manufacturing processes, binder jetting is a high throughput, low cost, and high energy efficient process. However, challenges with the process in terms of densification of bound preforms still exist. In general, additive manufacturing has many advantages over traditional manufacturing, most notably the ability to produce complex geometries and virtually any geometry without the need for a tool or a special setup. That being said, in binder-jetted materials, the fabricated parts in their green state, which we utilized, were determined to have a relative density of around 50% by using XYZ and mass measurements. Once sintered, a method of analysis known as Archimedes immersion density process was utilized to further accurately determine the exact density of each sample. Further specifications are displayed under the process subsection shown. Post-processing of sintering is required to densify parts to enhance mechanical strength, so the cubical samples are sintered at 1370 C at 7 different holy times at intervals including 0 hours, 15 minutes, 30 minutes, 1 hour, 2 hours, 4 hours, and 8 hours, as shown in tables 1 and 2. Holding time corresponds to the maximum temperature reading the sintering oven detects being held at that time for a specifically programmed time slot. After these After these same holding times were repeated for specifically sintered samples at 1220 C, it became evident that sintering temperature and density have a direct relationship. In other words, as displayed in figures 1 and 2, the increase in holding time results in a higher general density of each sample, which ultimately plateaus out after increasing at an exponential rate. Porosity is the main defect in binder-jetted materials. The majority of the large pores introduced during the binder-jetting process are attributed to the liquid-solid interactions between the binder and powder particles, such as the interlayer voids and printing lines caused by ballistic ejection. With this in mind, using the optical microscope, a total of 36 images were taken at set positions to determine the porosity of each sample. After micrographs like the one shown in Figure 4 were attained, an ImageJ software was then used to determine the average porosity. The dark spots suggest pores, while the lighter spots represent solid states. As displayed in Table 3, the average porosity and area decreases as sintering holding time increases. This corresponds to data determined using dimensional and Archimedes measurements. Powder-binder interaction leads to the formation of subsurface pores in printing parts. Therefore, a continuous gap between printed layers may be seen. If the powder dispensing system cannot eliminate the subsurface pores by adding newly deposited powder, defects will be transferred to the final part. By gaining designing experience, 3D printing, and characterization aspects of the additively manufactured parts, it was possible to determine the maximum density, or in other words, the lowest porosity, is attained when a sample with a green part density of roughly 50% is sintered at 1370 C for 8 hours, as compared to various 1220 C sintering times. Therefore, it was determined that sintering temperature and time have a direct relationship to the density of a material. This observation holds true until results level out and deformation of a sample takes place. Dimensional Archimedes and microscopic density values maintain consistency. The majority of the large pores introduced during the binder jetting process are attributed to the liquid-solid interactions between the binder and powder particles, such as the interlayer voids and printing lines caused by ballistic ejection. Further possible testing should be explored. With that being said, despite my major being mechanical engineering, the implications of materials and additive manufacturing are far-reaching, allowing me to incorporate all I have learned in my future studies and endeavors. Thank you for your time and this opportunity.
Hello, my name is Changyan Huang, and I did a research about physics of laser powder interaction in additive manufacturing using synchrotron X-ray imaging with Professor Amir Mostafai. The object of this research was to understand the dynamics of laser powder substrate interactions as a function of powder characteristic. Laser powder bed fusion is additive manufacturing technique to fabricate parts. It makes certain thickness of powder on a surface with roller or blade. Then the laser source melts the powder particles based on a CAD model. Common defects such as a lack of fusion porosity, keyhole porosity, and gas porosity can be observed, and these are the great challenges for part qualification. To overcome these challenges, synchrotron X-ray imaging can make it possible to observe the dynamic of laser powder substrate interactions and also understand the fundamentals of laser powder bed fusion and its various process parameters. Like in the pictures below, metallic powders are set between two glassy carbon plates while the laser beam goes through the powder. An X-ray beam penetrates the plates and powders to generate the X-ray imaging of the laser powder bed fusion process. With this process, we can observe the laser process such as generation of vapor cavity, melt pool, and porosity. In this experiment, we focused on measuring the depth of the keyhole. Keyhole is a deep, narrow cavity generated by a strong recoil pressure from the rapid evaporation of metal pushing the melted liquid down. ImageJ program was used to process the X-ray imaging video and to measure the keyhole depth. 3 types of powders were used in the experiment: porous powder, fine powder, and spherical powders. Different scan speed of laser from 0.4 meter per second to 1.2 meter per second went through the powders with same laser power. From the X-ray imaging, we could understand the pore formation mechanisms. Keyhole porosity is formed at the tip of the keyhole because of the evaporation of metal and gas entrapment inside the melt pool. Also, there were pores made underneath the powder layer, which were formed because of the low packing density and air pockets. From the keyhole depth analysis, as you can see in the graph in the middle, we found out that the faster scan speed results the shallower keyhole depth regardless of powder shape. Also, more fluctuation of keyhole depth was observed in coarse powder than other types of powders because it has a lower packing density. Finally, the fine powders results were almost the same with the spherical powders and turned out that it can be used to reduce the keyhole depth fluctuations. In conclusion, the depth of the keyhole decreased with increased scan speed for all types of powders. Also, keyhole can be controlled only by alerting the powder size distribution without eliminating the irregular powder shape. I would like to acknowledge 2 graduate students who helped me to collect, analyze data, and mentored me. Also, I acknowledge for financial support from our R&D program this semester. Thank you for watching.
Hi everyone, my name is Shelby Krager. I'm a second-year biomedical engineering student on the medical imaging track, and I'm going to be presenting my research on pancreatic cancer. So, pancreatic cancer is notoriously difficult to treat, with the most common form of this cancer being pancreatic ductal adenocarcinoma, which has an overall 5-year survival rate of about 8%. So the pancreas has a particularly dense extracellular matrix, and it's currently widely accepted that the extracellular matrix plays a large role in restricting drug delivery to these areas, thus reducing the efficacy of cancer therapeutics. So the main objective of this project is to explore this link between the makeup of the extracellular matrix and drug delivery by quantifying drug binding via the dual tracer method, which involves the co-administration of a nonspecific drug with a targeted agent. And we will also be measuring the makeup of the extracellular matrix via H&E staining. So the first step in this project was to grow the cells that we would later need for implantation. So the pancreatic cancer cell line ASPC1 was used for this project, and for implantation we need 1 million cells per mouse. So yeah, after we grew an adequate number of cells, the implantation process starts off with the anesthetization of the mouse, which is achieved by administering a mixture of isoflurane and oxygen, and then the mouse is placed on a heating pad in the right lateral recumbent position with a nose cone on to retain anesthesia, and a small incision is made, exposing the abdominal cavity. The pancreas is located, and the 1 million cells are directly injected into the pancreas. And then the incision is sutured closed, and the tumor is allowed to grow for 2 weeks before euthanization and extraction of the tumor for processing. So 24 hours before the extraction of the tumor, fluorescein is injected into the lateral tail vein of the mouse, and then after that 24 hours, the tumor is extracted and sectioned for imaging. So, yes. So the tumor is extracted and then sectioned for both imaging on the pearl system using the dual tracer method, and also for H&E staining. So if we look in the results section, the top left image is just a picture under the microscope of the pancreatic cancer cell line ASPC1 from when the cells were still being grown. And then just below that is the result of H&E staining of healthy pancreatic mouse tissue. So the hematoxylin stains cell nuclei a deep purple or blue color, while eosin stains the extracellular matrix and cytoplasm pink. So this allows for the differentiation and quantification of the different tissue structures within the sample. And then on the right we have a pancreatic cancer sample imaged via the dual tracer imaging technique, and ABY was used as the control agent in this image, and it's fluorescently labeled with IR800 dye, which appears green on the screen. So any of the green that's seen in this image is just from the control agent, which highlights the entire area of the tumor. And then Erbitux was labeled with IR700 dye, which appears reddish in the image. And so just with the naked eye alone, it is pretty obvious to see that the binding capabilities of this pancreatic cancer therapeutic is not where it should be, as the binding is not complete over the entire area. Yes, so currently in our project we are set to extract the tumors within the next few days and have the project entirely wrapped up and the data processed, but due to time constraints we're only able to provide you with this controlled data that you see in the results and discussion section. But thank you all for listening, and thank you to Professor Teshauer and Elif Nalbant for mentoring me during this experiment.
Hello, my name is Ryan Kroll, and today I will be discussing my research in investigating the role of powder characteristics of additive manufacture, Ti-64 structures for aerospace applications. To start off, additive manufacturing is one of many manufacturing techniques that leverages the concept of building parts layer by layer, which results in a three-dimensional structure. Laser powder bed fusion is an AM method which powder is spread across a build surface and solidified layers are made using a laser beam by fusing the powder together. Additive manufacturing is a unique manufacturing technique as it can fabricate complex geometry parts that other manufacturing processes cannot fundamentally achieve. AM also differs significantly from standard subtractive methods in that less material is wasted during the process. Despite the many tremendous benefits of AM, its primary drawbacks are its relatively high cost and time-consuming process. The key question that we are trying to solve is, can we use non-spherical morphology powder in laser powder bed fusion and take advantage of its benefits while developing techniques to minimize or eliminate its drawbacks? Now for Ti-64, it is a titanium-based metal alloy widely used in the aerospace industry due to many desirable characteristics, such as its high resistance to corrosion, high strength to weight ratio, easily heat treatable and weldable, and can withstand high temperatures. For the most part within industry today, parts are fabricated using fine particles, and these powders are spherical in shape. The reason this has been so common is due to two main advantages. One being the ability to have higher packing density, which I will discuss more in depth later on, but also due to its higher flowability. However, though, additive manufacturing is seen as a high-cost method compared to other techniques, and rightfully so, as fine spherical powders are very, very expensive. This is why additive manufacturing has been reserved mainly for lower production type processes. Spherical powder is more expensive due to its high production costs, and this correlates to the production of spherical powder being a high energy intensive process, which is less eco-friendly as a result. Another drawback for fine powder is, since it is smaller in size per particle, what occurs during the build process is something that is called spattering due to the ejection of these smaller particles. But how about coarser powder, which isn't spherical? So unlike fine powder, its production costs are significantly lower, thus more eco-friendly. It requires less energy to produce. Also, there is low spattering that occurs due to the varying geometry and the larger size of these particles compared to the fine ones. The catch, though, is coarse powder having a lower packing density, which leads to a significant portion of my research moving forward, which is developing techniques to increase the packing density of coarse powder. Hardness testing was done on sample materials from build conditions where as-built parts or as-built with post-processing done, particularly HIP, or what is also known as hot isostatic pressing. The hardness of a solid material can be defined as a measure of its resistance to permanent shape change when a constant compressive force is applied. Hardness has also a close relation to other mechanical properties like strength, ductility, and fatigue resistance, and therefore hardness testing for the AM samples were a simple, fast, and effective means in which to determine overall build quality, since parts are built layer by layer. In additive manufacturing process, key parameters influence the end result of a build. The parameters focused on in this effort are three main ones, being power, scan speed, and hatch spacing. We investigated various combinations of these parameters and ultimately found an optimal combination that resulted in 99.935% density. Density is important in manufacturing in general, but especially in AM because of shrinkage. For example, if a part is only 50% dense, then upon post-processing, which densifies the part by closing internal pores, thus reducing the final dimension of the part itself. Higher dense parts means more reliable parts, which have less defects and less post-processing is needed. In aerospace especially, tight tolerance are of essential importance, and having a large amount of shrinkage is not ideal and results in high likelihood of off dimensions. These internal defects of a build are known as pores or cavities within the microstructure of the part. These tiny pockets can entrap gases and are where stress concentration is high and results in lower lifespan of a given part. Porosity analysis, as shown here, illustrates the post-process of samples where you can see how significantly reduced and almost 100% elimination of pores within the initial build. Extending further on that is the essence of post-processing, which has contributed largely to the high cost associated with AM. This is why the less post-processing that can be done, the lower the end cost can be. Hot isostatic pressing, also known as HIP, is a post-processing method that basically applies pressure in all directions onto a part at very high temperatures. This helps reduces and nearly eliminates porosity within a part and results in greater than 99% density. Machining is also quite important as a supplementation to HIP, as it smooths and removes surface imperfections. Surface roughness is also another high stress concentration area, as the roughness can also be seen as tiny cracks where stress is high and damage occurs first, as those tiny cracks then grow and propagate throughout the structure. By smoothing the finish as much as possible, this improves fatigue life and part life cycle. Results shown are from fatigue testing done, first with spherical powder. As you can see, fatigue life is greatly improved with the combination of HIP and machining. To conclude this presentation, successful parameter optimization resulted in 99.935% density. In as-built plus machine fatigue samples, the surface roughness decreased, but still remains a chance for subsurface pores to remain on the machine surface and impact fatigue life. However, HIP treatment closes these isolated pores in the AM parts, and after machining results in a defect-free and smooth surface, resulting in a much improved fatigue life as seen below. Future work to be done would be continuing the development of powder packing techniques of coarse powder and the continuation of testing and analysis of samples leveraging those techniques. Thank you.
Hey, so my name is Fook Nguyen. This semester I was working in the robotics lab, and this was the project that I helped on this semester, which is a shape-shifting soft robot in space application. So this project has been developed before. It was earthbound though, so originally the orbs inside of the robots were jammed together using gravity, which would create a downforce on all the orbs, which would, in theory, kind of lock them together. And then from there, the project transitioned into an underwater application, which utilized a series of propellers to create negative pressure inside of the orb to kind of fill everything together and kind of jam it that way. This project, though, took the application into a vacuum environment. So utilizing either one of those applications before it was not possible. So there was three main possible potential design for it, one of which was the pressure chamber, which would pressurize the entire orb as a unit, and then it would slowly release air into a outer layer, which in theory would jam all of the orbs together. But the fatal flaw with that design is that the equilibrium state of the robot would just be a sphere. So this meant that for any application that required the maximum amount of force for the jammings to hold its amorphous shapes or all the unnatural shapes would be impossible, in that it would just revert back into the sphere. So it couldn't actually transform to morph around something. Only sections of it could actually morph around things. The second idea was having a bunch of tension springs that essentially would kind of pull the outer shell as if it's like a puppet. And then this would kind of straighten some parts and kind of morph around, kind of like a Pac-Man thing is what I originally envisioned. But the problem with this is that there is a finite number of strings, and we're trying to have this shape morph into an infinite amount of shapes. So Therefore, it is impossible for the soft robot to be truly soft and truly be able to wrap around everything if it's based around a bunch of strings that have a finite number. As for the final solution, which is the one we're hoping on testing and prototyping, is the figure here, which is a electric field on a smaller sphere on the inside and then a bigger sphere on the outside, and they would be opposing charge. So the inside would potentially be either negative or positive, and then the outside would be the opposing one. And essentially these electric field would pull towards each other, and that would create the necessary jamming force onto the orbs to actually lock the robot together and have it really jam. But this still needs a lot of testing, as in like actually fabricating and testing it in a vacuum and seeing if actually creates enough. We can actually create a big enough electric field that it would actually be significant in trying to jam the orbs together. The other issue is this could potentially be hazardous to other electronics that the robot might interact with. And then in general, just creating it in a 3D environment could potentially be difficult. So the next steps are to create a 2D model and test out the electric field before we proceed with anything else.
Everyone, my name is Anas. I'm currently a fourth year undergrad. I'm in the co-terminal program for biomedical data science and modeling, and my poster presentation is going to be on white matter integrity in Alzheimer's disease. MRI imaging is a non-invasive technique which allows for the visualization of inherent structural properties, microstructural properties in brain tissue. This is primarily based on water diffusion and the movement and the displacement of water in tissue. Fractional anisotropy is another common methodology for imaging, and it's based on even the diffusion tensor imaging, which is built upon diffusion weighted imaging. And these types of imaging procedures, they allow you to map and visualize neuronal axons and neuronal bodies within tissue. In this study, there were three groups of patients that were utilized. Number one, cognitively normal, CN. Number two was those with mild cognitive impairment, which is also an important precursor to Alzheimer's disease. And number three, Alzheimer's disease patients themselves, AD. Statistical analysis was performed on these three groups, and there was specific additional care taken to prevent any inclusion of false positives, because as the number of the number of analysis we performed just increases, we also have a higher risk of false positives being included in skewing our data. Moving on into the methods, number one, we had to acquire the data from the Alzheimer's Disease Neuroimaging Initiative and load this data into Python. Afterwards, you had to extract subject labels and group these various groups together. So subject labels were a reference to each reference subject ID. So it would tell you whether or not a subject was cognitively normal, whether they had a mild cognitive impairment, or whether they had Alzheimer's disease themselves. So you had to group these three together to create three matrices of all the subjects, CN, MCI, and AD, and then perform voxel-wise statistics on these three matrices of subjects. So afterwards, after you perform the voxel-wise statistic, you would get back a test statistic, and you would get back a p-value. And false positive prevention deals with limiting the p-values based off a certain threshold, which is the critical q value, which is computed to the Benjamini-Hochberg procedure. And so a mask was created where the p-value satisfied the Benjamini-Hochberg procedure, and the value for those p-values would be turned into a 1, otherwise it would be a 0. And this would just signify the locations which we're going to be using later on. So the voxel-wise Cohen's group differences were also conducted, and that's effectively taking the difference between two groups' means, so between cognitively normal and Alzheimer's disease, or cognitively normal and MCI. You have to then divide the difference between means over the standard deviation. And the standard deviation was a pooled standard deviation because the three groups had different number of subjects. You mask this voxel-wise confidence group difference with the p-values mask. So you only use the areas where the p-value passes the threshold, so that we know there's a less of a chance of a false positive being included. You turn that back into an image to view in FSL Viewer, and the results are below. So figure 3, 4, and 5, they're of the same image, except they're taken from different angles. So we have the lateral view, we have the front view, and we have a top-down view. And you can see that there's overall a larger Cohen's group difference, CN/80, and that's represented by the reddish color over here, and over here on the outskirts. Over here, you can also see the same thing, and over here, it also is showing the same thing. Now, what exactly does this mean? The Cohen's group difference, the higher the Cohen's group difference, the higher the effect size, and the effect size is important. It's a very powerful statistic because it shows how there is a clear distinction, there's a clear difference between the patients who are cognitively normal and the patients who have Alzheimer's disease or mild cognitive impairment. Taking a look at figure number 6, you can see the distribution I've drawn over here. The yellowish curve represents the Cohen's d for all the cognitively normal and mild cognitive impairment subjects, whereas the blue represents the Cohen's d for all the cognitively normal and the Alzheimer's disease subjects. Once again, you can see that the Cohen's d is larger for those that are cognitively normal and Alzheimer's disease. And this is in line with what I represented in the results over here. So to conclude, the Cohen's group difference provides an efficient way to accurately be able to visualize the differences between groups. Overall, we've seen that patients with progressive Alzheimer's disease have had larger Cohen's D's, a greater effect size, and which is more centralized in the corpus callosum region. And the results are confirmed from the distribution over here. Future directions consist of repeating this process for PET data, positron emission tomography, and the current work has been done to acquire a pipeline for PET data analysis, the clinical pipeline. In addition, future work is also going to be directed towards developing an imaging biomarker which can accurately depict changes in white matter. Thank you so much.